So work is basically is said to be done when an object moves a displacement in the direction of the force applied to it. Now, this is very important, and the key word is that it's basically moves a displacement in the direction of force. Okay, so let me just uh, explain it in a bit. So what happens is that work is force times displacement, and the SI units for work are joules. Work, by the way, is a scalar quantity, and now in different cases we'll see how work is done and when work is not done. For instance, the simplest thing is that if we push a box, suppose this is a box, you apply a force on this box, and this box basically moves a certain distance. So when it moves a certain distance, we can say that work is done because force times displacement or equal to force times the displacement it has moved. Now, in a similar case, case 2, so suppose this is Earth, and around Earth there is a satellite that is moving, obviously in a circular motion. So the satellite feels the force towards the Earth, but it's moving in this direction, I guess. Do you guys think work is being done? Anyone? Okay. Yes, please. Anyone who has an idea? Yes, work is done. Why? How work is done, Shazid? So in this case, remember that work as there is force. No. In this case, you need to remember that work done will be zero. And the reason why it is zero, because the force and the displacement are not in the same direction. They should be parallel to each other. Because force and displacement are not parallel. They must basically be in the same direction or against it. In this case, neither the satellite will move closer to Earth nor move away, so it's not possible that it's doing any work. Is it clear now? Now, the next. So, one of these things in case 3 that we're going to see is when, suppose this is a slope, and there is an object like this. All right. So naturally, we'd say the weight of the object is gonna be down. Now, I told you in the forces chapter how to resolve these forces on a slope. I hope you guys remember. So if we say that this to this distance is s. Now this distance and the force are not actually sort of in the same direction. So what you can do is you can make components of it. So if this is angle theta, so how did we make components? Let me remind you. We used to make one force, one component down the slope of this force, and one component perpendicular to the slope, like that. I told you that the angle of the slope is the same angle as this one, which means that this force is going to be W sine theta, and this going to be W cosine theta. So if I want to find what is the work done when the object moves from this point to this point, I would say that you have to find that force which is parallel to it, which means now work done will be equal to W sine theta times the displacement. Anyone who could not understand this, please let me know. ऊपर ना पानी की बोतल भी है, वो असल में काली गाड़ी है ना, नीचे खड़ी, वो काली गाड़ी में पड़ी हुई है, उसको लिया जी. All right, is it clear? Anyone who did not understand this? Imal, Asma, Caroline.
Those.
Now, interestingly, if I had, if I knew this height, because this is the same height it goes down, so I would have then so if I had this force, I had this distance h, then the same work done could have been formed, could be like found out by the force that is parallel to this height. So this force W is parallel to this height. So then we would take work done to be W times h. Do you guys get it? All right. And these two are basically the same formulas. How do I know this? Because if you look at this is a triangle, and this is the opposite, this is the hypotenuse. All right, so I'm going to write it down. So we already know that sine theta is opposite over hypotenuse. So sine theta will be equal to h over s. You guys agree? Now check this out. If I replace this sine theta with this sine theta, so it's going to be W times h over s, so I placed it, times s. So ultimately you see it is going to give me the same value as this. It doesn't matter. So you just need to look at the right height or the distance, because when you find that distance which is parallel to the force, which means now you can easily find work done by just multiplying those. Yes, Yasir, Zilba, Fatima, everything is clear. I wonder where is Farina today. Okay. Yes, sorry, Furkan. I forgot your name.
Yes, sir.
Good. Now, so to do all this work, obviously you need to have some energy. This is the reason we take energy and work as one. Because energy, when we define energy, we can basically write that it is the capacity to do work. You do not have energy, obviously you cannot do work. So then the SI units of energy are joules, and obviously these are scalar quantities. Understood? Now, let's go forward. Just a second, please. Okay, so there are different types of energies. Let me just write that down. First of all, we got potential energy. Potential energy has further three types. The first one amongst these are, write it down, elastic potential.
वही हमने देखे हैं लड़की ने पैर भी घूमते नहीं है।
अच्छा,
हाँ जी
फिर वो ऊपर पड़ी होगी शायद कॉमेंट में।
वो जो उधर लड़का है उसने खोली गाड़ी अच्छा
ठीक है, मैं देख लेता हूँ।
ये चल
Gravitational potential, and then you have the third one, which is known as electric potential. So all these are basically types of potential energies. Now, I'm going to explain these one on one, but first let's just complete the list. The next one we have is kinetic energy. Then we got chemical. Then we have thermal. Then we have light. We also have sound. Then we have nuclear. Like that. All right. Now, when it comes to elastic potential is due to the change of shape of a body. So if you compress something, you stretch something, whatever you do, that causes that basically stores elastic potential energy. Then gravitational potential is due to the attraction of gravitational force or work done against that. Then this is due to electrical movement of charge. Finally, we have kinetic energy. This is due to movement. Chemical energy is basically stored energy in chemical reactions. Then we have thermal energy, which is basically heat energy. It's also known as internal energy. Finally, we have light, which is energy carried by photons. We have sound, which is energy due to longitudinal waves. Finally, we got nuclear, and nuclear is basically energy due to fission, which is basically splitting of an atom, sorry, nucleus, or fusion, which is combination of like combining of a nucleus, like that. So you guys can please copy this. So if they ask you about any of these, you should be able to remember. Now, all right. Now the next thing we're going to look at, these things all already you might have done it in O levels. It's not a big deal. So we're going to now do law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed. It can only change from one form to another, like that. Remember, in physics, laws do not break. Laws means that it is going to always happen. Anyway, so we look at an example here to see how this is applied. So it states that a trolley, oh my god, starts from rest at X and reaches Z and comes to rest. Okay. Now they say write the energy changes in this process. Okay. So they have shown basically a path like that. This is X, this is Y, this is Z. Now they have shown a trolley that basically moves through all this path, and when it comes to this point, its velocity becomes zero as well. Now remember that this height, which let's call this h1, is bigger than this height, which is h2. All right. Now we need to write this. So first of all, we need to understand that you see it doesn't reach the same height. So can somebody please tell me what kind of energy will it have at the at x when it has no velocity? Yes. Anyone? That's not fair. Yes. It would be gravitational potential. That's correct, Shazib. Thank you. So initially, we would say when it's moving from x to y, it's gravitational potential energy. And now, obviously, it will lose that height to reach y, which is the lowest point. In which forms do you guys think this energy will change? Okay, kinetic energy. And would it only change in kinetic energy?
Thermal energy.
Yes, it is going to heat. It's going to lose some of the energy to the surroundings form of heat, because at the end we see it's not reaching the same height, so it must happen. Anyway, from Y to Z then, what do you think would be energy changes then? So what is the inertial energy it has? So it's moving, and because of movement, we can say it is kinetic energy. And now kinetic energy is gaining height again, is changing to what? Gravitational potential. Very nice. Plus, obviously, heat will be lost whenever it's moving because of the friction, obviously, on the path, right? So you guys need to remember that each change should be written when they ask you to do that. And please think hard what is happening when they do that. All right. If you guys have any questions, please let me know here. All right. So the next thing that we're going to do is a very, very important. You guys have copied it? Anybody who's left, please let me know. Should I go forward? Okay. So the next thing we got to basically uh, do is, in our course we have the formulas for gravitational potential energy, but not just formulas. We also need to derive these formulas. So the derivation is included. The derivation for this one comes for only 1 mark. So still you don't have to lose that. So for this one, you guys need to remember that work done is force times displacement. We know this. We also know that force due to the gravitational field is equal to weight, which is mg. So we're going to write that. And whenever we lose or gain gravitational has to be an involvement of change in height, which means you got to either gain it by going up, you got to lose it when you are going down. So we're going to plug in the values. So the work done would be equal to, instead of force I'm writing mg, and instead of height, instead of displacement I'm going to write height. So the gravitational potential energy would be mgh this way. Okay, so this is a very small derivation, just 1 mark they give it for, so just look at it. It's not very hard as well. Okay. Now, the real deal basically comes when they give you the derivation of kinetic energy that we're gonna just look at now. So for kinetic energy, the derivation would be of 3 marks, and this one is a bit harder, so you guys need to follow along what I do. Okay. All right, kids. So first of all, for this one, if you don't do this, it's okay, but I would basically recommend that on the side you make a small, um, say, make a graph, okay, of velocity and time. This graph will start from 0 and it will be a straight line. This will be the initial velocity as 0, mark it as final velocity as v, and take this as time t, okay, like that, when the velocity was v. So when you make this graph, then first you're going to say that work done is force times displacement. Also, we know that force is equal to ma, right? We all everybody I hope knows this. Which means if I plug it in right here, so work done will be ma times s, like that. So you got this equation, okay? Now, in the next part, we already know that 2as is equal to v square minus u square. We know this. We are going to make s the subject of the equation, and if I do that, it's going to be v square minus u square over 2a, just like that. If anybody doesn't understand what I've done, please let me know. Okay. Now, you guys can see that since u initial velocity was 0, so I can basically write this equation as s equals to v minus 0 squared over 2a, which makes s to be v squared over 2a. So I've done this on side, all right? Then you're going to add this right here, and when you do, it's going to be ma times, instead of s, I'm writing v squared over 2a. Any questions here? Please let me know. You see, acceleration and the acceleration here just cancels out. And when it does, you're only left with mv squared over 2, which translates into half mv squared, which is basically known as the kinetic energy. If you have any questions about it, please let me know. I can do this again if there's an issue. Because this is a major 3-mark derivation, I don't want you guys to get it wrong in the exam. Yes. Fatima, everything is clear. Caroline, Asma, Himal,
Yes, sir.
Yasir, Shazib, and Zirwa. Please look at it carefully. Okay. All right. Very nice. Very nice. Good job, people. Sorry, Furkan. Furkan, everything is clear?
Yes, sir. It's clear.
Furkan, you gotta change your name. Why does it say yes, am? What does that mean? It's very confusing. Anyway, now on to a challenge question now. Let's see if you guys can do it, okay? So, I think I would want to go to the next page. If you guys had done this, I want to move there. Okay. Now, so this question is a challenge question for you people. Let's see how many people can do this. A small mass is released from rest at point P on a frictionless smooth hemisphere. All right, so it's basically like this. Okay, and then they've shown a couple of points. It being here, then here, then here, then here, and at the bottom, right here. Okay. And they've given you the velocities as well. At this point, the velocity is 0. It's called P point. At this point, the velocity is 1.0 meters per second. It's Q. At this point, the velocity is 2.0. At this point, velocity, oh, this was basically EQRS 3.0. And at this point, the velocity is 4.0. And this is T. Okay, so they're giving you this. Now they say that the mass loses gravitational potential energy E in falling from P to T. Now they say at what point amongst P, Q, R, S, T, the mass has lost GPE by 4 times. Can you please try this? See if you guys can tell me the point. Yes, anyone got an answer?
So is it at R?
At R. All right, that's correct. It is definitely at R. Anyone else who got the same answer? Asma, could you do this? And Caroline, Fatma? Zirwa, what about you? Yasser, Shazid? Sorry, Furqan, Shazid? Okay. Now, basically, it can be done in two ways. All right. So I'm going to tell you both of them. So, first method to do such questions, where basically there's the same object and he's asking about energies at two different points. So, please write method one. Now, this is the simplistic method where you know that obviously because it is falling, so the GPE lost will go into kinetic energy, right? It is gained. So we know that kinetic energy is half mv square and GPE, let's call this E, all right, for just now, or just write GPE. So now, what you guys need to remember that because it is the same body, so half and mass are constant values. At each point that they've given, half and mass is not going to change, only the velocity is going to change. And when the velocity changes, obviously GP is lost, right? So it means that we can build a relationship here, and the relationship would be that gravitational potential energy would be proportional to V square, right? Whatever it is lost. So whenever a relationship creates, what you guys can do is you can simply write that gravitational potential energy at one point over gravitational potential energy at the second point will be equal to the velocity at the first point over velocity at the second point. So this is how I can create any relationship. It could be any formula, it doesn't matter. So what you're going to do is you can basically check which two quantities are changing, and then you can make a relationship between them like that, right? Now, it said that E is it basically loses E when it has fallen from P to T. So at P velocity was 0, T the velocity was 4. So which means that the energy E was lost when the velocity was 4. So I'm going to take whole square. We want to find what will be the velocity when E by 4 was lost. So we got to find this velocity V2. And then we can pick which point it was at, right? So 4 will basically go on the top. So we can write 4e because it's double dividing, divided by e. 4 square is going to be 16 square times v2 square. E and e is going to cancel out. So v2 square is going to be, oh, I had to write 16, sorry. 16 divided by 4. So v2 square is going to be 4. You take the root, and V2 will come out as 2 meters per second, and 2 meters per second is at R. So I can say, okay, is it at R? Do you guys understand this? Please look at the solution and let me know if you guys have any questions here. All right. The other method of solving this would be by taking any supposed mass. So what I can do is, so you guys can see, the thing is that because the mass has no effect on how much GP is lost, so we can basically make a relationship. Again, I'm going to write that gravitational potential energy lost will be equal to kinetic energy lost. And I'm assuming that mass is 1 kg. It doesn't matter, I'll tell you how. So GPE then will be equal to half mv squared. So what I can do is to find E, the total energy lost was E. So I'm going to put 1 instead of mass, and I'm going to put 4 here like this. So it's going to be basically 16 divided by 2. So the energy, if the mass was just 1 kg, would have been lost by 8 joules. So I have this answer. Now what I can do is I can write that what will be the speed at E by 4. Okay, so this is what I want. So I know that the E is 8 joules, my bad, E is 8 joules. So I can say E by 4 is going to be 8 by 4, which is just 2 joules then, because a quarter of 8 is 2, right? Again, I'm going to use the same technique that the gravitational potential energy lost will be equal to kinetic energy gained, which means I can write 2 joules was when 2 joules was lost, what would be the velocity at that point? Again, just put the values half. Instead of mass, let's write 1. This is v squared. 2 will multiply on that side, so it's going to be 4. This is v squared, and take root now. So v is going to be 2.0 meters per second, and that would be at r. So whether you're doing with the relationship or you're doing with the like supposed value, you will end up getting the same answer, because again I'm telling you, if it's the same mass, the mass doesn't change, then at all points the mass would be the same and its speed would only affect gravitational potential energy, nothing else. If you have any questions, please let me know here. Okay, yes. Imal, Asma, everything is clear?
Yes, sir.
And Caroline, what about you? Fatma? Okay. And Shazib, Furqan, Zirwa, any questions you guys have? Furqan, are you there? All right, then, you people. So we'd stop here, and in the next class, basically, I will be checking your worksheet. Make sure you do that, and then if the time is left, we'll complete this chapter because only power and efficiency is left. All right, I will see you then. Have a great weekend. Bye.